Okay, so we looked at laminar and turbulent boundary layers for external flows previous lecture, and in particular we looked at mass and momentum thicknesses and touched briefly on separation, but we were restricted to flat plates. So in this case, this lecture, what we're going to do is to start looking at the pressure distribution around an object, and what we find is that the pressure distribution is actually a form of drag, and this comes into designing correctly shaped objects. And for instance, it's why cars are all roughly the same shape these days. So we've looked at wall shear stress in terms of simple flows that are not changing direction, so couette flow, pipe flows, and flat plates. Okay, but we know in real life when we have curvature in the flow, we can get lots of different types of flow patterns behind an object. So the classic example is a cylinder, and depending on the Reynolds number you can get different flow patterns behind this object. So very low Stokes flow, you get streamlines that stay stuck all the way around. You can get a small separation zone, you can get a larger separation zone with the laminar boundary layer, and this is what we see here. And if it was a turbulent boundary layer, the flow would stay stuck further around, and you get a smaller wake, and as we'll see, you get a smaller pressure drop, a smaller drag on the object because of this. So one technique is to use roughness to trip a laminar boundary layer to make it turbulent, and this essentially is what golf balls do. Okay, so let's start thinking about what happens to pressure as you start making a flow go around an object. Okay, so we've got our aerofoil here, and we're going to follow a streamline that is forced around it like this. Okay, and essentially when the flow is pushed around the object, it's accelerated in this region. Okay, and as it's accelerated, the pressure must decrease to keep the stagnation energy the same, and then it gets to the thickest part of the aerofoil, and then after that the velocity will relax. Okay, so the velocity is slowing down here and the pressure is going up. Okay, and so when we plot the pressure as a function of the distance along the streamline, we find that the pressure profile looks like this. So this is where the flow is being accelerated around the object, and this is where it's slowing down and the pressure is starting to recover. Okay, and if you remember from the Euler equation, the pressure gradient is a force. Okay, so when we've got and if you look, this is the sort of the maximum point, and when we look at the pressure gradient here and here, the gradients have different sign. Okay, and the gradient gives you the direction of the force. So here the pressure is pushing the fluid onto this surface. It's trying to so there's no chance of the fluid separating. But here, effectively, there's a force trying to push the fluid in the opposite direction it wants to go. And this can cause instability, and it's this region that can cause separation. And this is why if you're going to design an aerofoil, you have to think very carefully about where it will separate. Okay, so separation typically happens when there isn't any shear stress. So this is a separating flow, and effectively there's a force pulling the fluid in this direction. Okay, so this the fluid up here has a lot of momentum, carries on, but the fluid near the boundary is going much less fast, and there is a force pulling fluid from right to left, and effectively you can define a separation point where the shear stress goes to zero, so where the velocity gradient goes to zero, and behind it you can start to get reversed flow. So flow is being sucked in from downstream because there's no the forces effectively balance at this point. Okay, and laminar boundary layers are much more prone to separation than turbulent boundary layers. Okay, and this is a big issue when it comes to looking at the drag characteristic of objects. Okay, so next thing we want to do is just to try and understand how pressure can influence drag. So the key thing to understand here is that for any object moving through a fluid, there are two forces at any point. There is a viscous force that's always parallel to the surface, and there's a pressure force that's always normal to it, and both of these are responsible for lift and drag of an aerofoil, say. Okay, so you can take and you can have any one of these elements all the way around. So if you take one of these elements, you can work out the viscous force and the pressure force, and then you can take the x components of these forces and they will contribute to the drag, and the y components of these forces will contribute to the lift. Okay, and so you do this for one area element, and then you add it up all the way around, and you can work out the total drag and the total lift. An aerofoil typically is characterized by a drag coefficient and a lift coefficient for a certain angle of attack. Okay, and so how you design your aerofoil really comes down to what you want in terms of your drag lift characteristic for your aerofoil. And why is this important? Well, it dramatically influences the drag characteristic. So with this kind of graph, what I want you to be able to do is to try and understand what's going on here. So we've got the y-axis, which is the total drag, so this is the friction drag and the form drag divided by the kinetic energy, and the x-axis is the Reynolds number. And let's look at the circular cylinder first of all. So this is very low Reynolds number, and this is where it's in Stokes flow, where the streamlines are sort of symmetrical fore and aft, and then we start to get separation region growing, and then we get a stable laminar separation point. The drag sort of stays roughly the same for a while, and then the boundary layer goes from a laminar to a turbulent state, and the wake gets much smaller, and you get this huge drop in drag. And then if you keep increasing the Reynolds number, the separation point for the turbulent boundary layer starts to creep back round to the side back up to sort of the pole position, and the drag starts to rise again. Okay, so I want you to be able to try and explain what this curve does in terms of the boundary layer and the drag. And if you can start changing the objects, if you can start changing, for instance, the separation point, then you can control very much the drag characteristic. So if you have a streamlined shape like this, you're actually greatly reducing the size of the wake coming off, because it doesn't really want to separate, and it will separate quite late, and this keeps the wake much more narrow, and you get a smoother drag characteristic for a streamlined struck, and it's much less drag. So some people design objects that are called bluff bodies. So these have shapes. So let's take, for instance, the square rod. So these have corners on them, and what happens when you have a sharp corner is, regardless of the flow, more or less, you always get separation on these points, and the drag characteristic and the separation doesn't really change with Reynolds number. So they generally generate more drag. So bluff bodies will generate more drag, but they have the advantage that you know what the drag is going to be. You don't get this very complicated drag characteristic for a circular shape. So if you're trying to design something that's going to move through a fluid, it can be, if you want to control the motion, controlling where the flow separates can be very advantageous. Okay, so just to sort of try and summarize this in terms of how we do this as engineers, obviously drag is really important. We burn a lot of fuel getting objects to go through fluid, and there are design compromises. So the classic one is sort of cars and aircrafts and ship. So for cars, so when we started off building cars, we didn't really care about anything really, and so they were little boxes. From a drag characteristic, they were terrible, and they started getting down to around about 0.3. So you'll notice that these ones are 0.3, 0.31, 0.3, 0.20. So, and we get down to about 0.27, 0.29 these days. And and nobody really wants to buy something that looks like a spaceship, really. So people want to buy cars where they can see the wheels, for instance. But having wheel covers dramatically improves the drag characteristics, for instance. So you have to design within the limits of what you need to do. Aircraft, it's not just a drag, it's a lift. Wings are obviously designed to do something, so you have to work out what it is you want to do. Is it a long haul aircraft? Is it a fighter aircraft? And so on. And so for ships, pressure drag is effectively negligible due to this huge flat surface that you've got on ship hulls. So for ships, pressure drag is a non-issue, but roughness very much is. And so how to try and keep your hulls clean really is kind of key to trying to keep your fuel efficiency high. Okay, so we've looked at separation quite briefly and tried to introduce how pressure can change the drag characteristic quite significantly of an object. Okay, thank you.